Welcome to Mrs. Z's Chemistry. In this video, for 6.1, we will learn about electromagnetic radiation. In many situations, light doesn't behave in a way that can be explained by a particle. Light often behaves more like an electromagnetic wave. In fact, visible light is just a small portion of a very large spectrum of waves that we call electromagnetic radiation, or EMR. Visible light and many other forms of EMR can be used to infer the energies of electrons within atoms and molecules. This is why this topic is important in our study of chemistry. Much of modern technology is based on EMR, or electromagnetic radiation. For example, the way your microwave works, or radio waves from your cell phone, X-rays used by dentists and radiology technicians, Wi-Fi and radio transmitters, as well as light from your TV and phones, and much more. So this wave is how the energy is transported from one point in space to another. Thinking about shaking the end of a rope, this transfers energy from your hand to the other end of the rope. Or dropping a pebble into a pond causes the waves to ripple outward along the water's surface. All forms of electromagnetic radiation, or EMR, have characteristics similar to water waves. All waves, including electromagnetic waves, have peaks, which are sometimes called crests, and troughs or valleys. We can describe the wavelength to be the distance between peak to peak or trough to trough. It is measured in meters or kilometers if very long, or nanometers if very small. The frequency is the number of wave cycles that pass a specific point in space over a specific amount of time. A cycle corresponds to one complete wavelength, from peak to peak. Unlike water waves, which can travel at different speeds, electromagnetic waves all travel at the same speed, no matter the type of electromagnetic radiation we are looking at. This speed is called the speed of light. Here is the unrounded number calculated with 9 significant figures. However, in our calculations, we will just be using 3 times 10 to the 8 meters per second. The seconds in the denominator mean for every 1 second, the wave travels 3 times 10 to the 8 meters. To better understand how fast this is, let's convert this into miles per hour. Pause to see if you can do this on your own first. So here we have the speed of light. We are going to write the meters in the numerator and the 1 second in the denominator. First, let's convert our meters to kilometers. And it looks like my formatting is slightly off here. But then convert our kilometers to miles. Miles should not be canceled because that is the unit we want in the numerator for the answer. Then let's cancel our seconds and cancel the minutes, and we're left with hours in the denominator. When you multiply across the top and divide across the bottom, you should get 6.7 times 10 to the 8 miles per hour. Written out, that looks like this, 670 million miles per hour. This is how fast all forms of electromagnetic radiation are traveling. This includes visible light, X-rays, microwaves, radio waves, all of them. Let's discuss the wavelength and frequency of EMR a little more. In equations, the wavelength has a variable that is a Greek letter, lambda, and it looks like this upside down Y here. Wavelength is measured from peak to peak, like from here to here on the wave, and the unit is often meters. Frequency has a different Greek letter for the variable, and it's called nu, and it's this italic looking V. This is cycles per second. The unit seconds is in the denominator and can be written as s to the negative 1 or 1 over s, which is all equal to 1 hertz. Frequency describes how many times the wave travels from peak to peak in 1 second. Because all EMR travels at the same speed, the speed of light, wavelength and frequency of electromagnetic radiation are always related with this equation. This equation is on the back of your periodic table, of course. In problems, if we are given just the wavelength of the particle type of EMR, we can find its frequency because we will always have the speed of light, which is c, in this equation. Again, here's wavelength, and then here's frequency. Let's rearrange this equation to solve for either wavelength or frequency. If you divide wavelength on both sides of the equation, we would look like this. So frequency can be calculated by taking the speed of light and dividing by the wavelength. Or you could take the speed of light and divide by frequency to solve for the wavelength. Before we do a couple of examples, let's look at this slide. This picture shows the electromagnetic spectrum in order of decreasing frequency, which is moving to the left, and increasing wavelength, which is moving to the right. We'll look at energy in a moment, but energy and frequency move to the same direction. Increasing energy and frequency move in the same direction. So we typically consider the electromagnetic radiation with the longer wavelengths to the right of this picture, the right of the visible light, to be harmless. So when we're looking at this, we can see radio waves and cell phones and microwaves from microwave ovens and wireless transmitters, as well as TV remotes and night vision goggles using infrared. All of these on this side of the picture are generally considered to be harmless. To the left of the visible portion of the spectrum are considered to be more harmful on this side. This is why it's important to wear sunscreen when you're out in the sun and being exposed to ultraviolet radiation or UV rays from the sun. As well as when you go to the dentist and get x-rayed, they often put a heavy metal apron over your organs to help protect them. In science fiction, these gamma rays over here is what created the Hulk, but that wouldn't happen in real life. Let's look at our first example problem. A sodium street light gives off yellow light that has a wavelength of 589 nanometers. What is the frequency of this light? Pause to see if you can work this out. Let's look at our equation. Right here we have speed of light is equal to the wavelength times the frequency. We are given the wavelength. We know that it is the wavelength because the problem describes it as wavelength, as well as the unit is a distance unit. Meters, nanometers are both distance units. So if we divide wavelength on both sides of the equation, we're going to solve this. The speed of light divided by the wavelength is equal to frequency. So here's the speed of light in the numerator. Our wavelength is in nanometers, so let's go and convert to nanometers. We have meters, 10 to the negative 9 meters, or a billionth meter, is equal to 1 nanometer. Our wavelength of 589 must show up in the denominator. We must divide by it because of the way the equation is rearranged. Plus, we also want to cancel our nanometers. We don't want any meters or nanometers to show up in the answer. We're asked for frequency, and the units for frequency should be seconds to the negative 1, which means seconds in the denominator. When we multiply across the top and divide across the bottom, this should be the answer, and we're left with just seconds to the negative 1. Another way to set it up is to first convert your 589 nanometers to meters, like this. And then, because of our equation, you're going to put speed of light on top, the c, and then the upside down y, or the lambda, is your wavelength converted in meters in the denominator. Then you divide. You can see that your meters cancel, and you're left with seconds to the negative 1. This is the exact same math, just set up a little bit differently. Pause and work this second problem out before seeing the answer. In this problem, we were given a frequency. We know that it's frequency because the problem described it as frequency, and also the unit is megahertz. Anything with hertz or seconds to the negative 1 is a frequency unit. So first, let's look at our equation. We are now given frequency, so we're going to take c divided by frequency, and that equals wavelength, which is what we're solving for. Convert our megahertz to hertz. 1 megahertz is a million hertz. When we multiply, we get this value, 8.5 times 10 to the 8 hertz. 1 hertz is equal to 1 over seconds, which can be written like this. So we have a 1-to-1 ratio between hertz and seconds to the negative 1. C, or speed of light, is in the numerator. Frequency is in the denominator. These seconds cancel, and we're left with meters. 0.353 meters is the answer to this problem. Sometimes light displays behavior like a wave, and other times it displays behavior more like a particle. This is called what scientists call a wave-particle duality. When light is behaving more like a particle, we call them photons. When substances are heated, they can radiate some of the excess energy as light in the form of photons. Photons produced in this manner have a range of energies and thereby produce a continuous spectrum in which an unbroken series of wavelengths is present. Most of the light generated from stars, including our sun, is produced in this continuous spectrum fashion. You can see all the visible wavelengths of light present in sunlight by using a prism to separate them. Sunlight also has shorter wavelengths, UV light, as well as longer wavelengths, infrared or IR light, that we can't see with our eyes, but can be detected by instruments. In contrast to continuous spectra, light can also occur in discrete line spectra. Exciting a gas, which means heating the gas under certain conditions, adding energy to it, will produce line spectra. This is how neon signs operate, and we can see individual colors this way. Each emission line on these barcodes of light consists of a single wavelength of light, which implies that light emitted by a gas consists of a set of discrete or specific energies. Each element has its own identifying barcode of light. 4 of them here, sodium, hydrogen, calcium, and mercury, are shown here. This is called spectroscopy, and it is a very precise science, which means the wavelengths of each element are measured to a very high degree of accuracy. So now let's discuss how we can find what discrete or specific energy is associated with a specific wavelength or frequency. Exciting a gaseous element means to add energy to it. Energy has a variable of capital E, and usually the joules or kilojoules are the units for energy. So we have this equation here. E is the energy of one photon or one particle of light, and it's calculated by taking H, which is a constant here, 6.626 times 10 to the negative 34, with joules and seconds both in the numerator. Take H and multiply it by the frequency of the photon, which again is what we've just been looking at. Has a unit of s to the negative 1 or hertz. If you take our equation of the speed of light is equal to wavelength times frequency and solve this equation for frequency, we have speed of light divided by wavelength. And if you take this portion of the equation and substitute that in for frequency into our energy equation, we get this equation. Energy is equal to h times c, so Planck's constant and the speed of light in the numerator multiplied together, divided by the wavelength. The wavelength better be in meters here because our speed of light has a unit of meters. All right, so now we just have 2 more practice problems left. When we see light from a neon sign, we are observing radiation from excited neon atoms. If this radiation has a wavelength of 640 nanometers, what is the energy of the photon being emitted? Think about what you are asked for. You're asked for energy. Find an equation that solves for energy given wavelength, since that is the other variable we're given in this problem. Here's the equation we want to use. We need to convert our 640 nanometers into meters. Here's the value of 640 nanometers in meters, 6.4 times 10 to the negative 7. Our numerator has h times c. And the denominator has our wavelength in meters. The units cancel, and we're left with joules as the only unit left, and that is fantastic for energy. 3.1 times 10 to the negative 19 joules. And this is per photon has this teeny tiny amount of energy. Here's the last problem. Pause to work this problem out before seeing the answer. Because in this problem, we're again asked for energy, but given a frequency, this is the equation we'd like to use. Take your Planck's constant, which is h, times the frequency. Because 1 hertz is equal to seconds to the negative 1, we don't have to use a unit conversion as this is a 1-to-1 ratio. Multiply, and we get this answer. Because our original measured number in the problem only has one significant figure, our answer should only have one significant figure. You can now complete problem set 6.1. For the first few problems, you'll need to reference this chart here or a similar chart that you can find on Google.